Hi, everyone. I'm Abhishek, and this is my submission for the Vanguard track, a quantum allocation and staffing co-pilot. So, addressing two problems with one shared pipeline for portfolio construction and call center staffing, both formulated as QUBOs, both validated the same rigorous way, and both tested on real IBM hardware, not just simulation. So, before the details, here's the method I held myself to for every result in this deck. Formulate as a QUBO, validate against brute force, solve it both classically and with QAOA, then stress test at increasing scale. Uh, One point, I want to flag this now because it matters for how you read everything that follows. Every QAOA number here was cross-checked against an exact classical solver before I trusted it. That discipline caught two real encoding bugs during development, which I'll walk through, not hide. And I tested 7 circuits on real IBM hardware, Fez via the Classiq IDE, not just simulator numbers. So coming to the judging criteria, given the rubric is speed, optimality, and scalability, I didn't want you to piecing that together from 20 slides. This is a map. Speed is addressed on the scalability slide and the disruption resolve slide, optimality on the two baseline validation, scalability on the scalability sweep, and the mixer circuit slides. Every claim after this is traceable to one specific measured result, not a summary, I'm certain. So I want to be upfront about the actual motivation because it's not what people usually assume. This isn't a claim that quantum beats classical today. Classical brute force search grows exponentially with problem size, and at our test scale, like 12 assets choosing 4, that's 495 combinations. It's trivial though, but at institutional scale, 500 assets choosing 50, that's 10 to the 60th power. Physically impossible to enumerate. So QAOA's qubit and gate count only grows linearly. That's a real long-term argument for quantum here. But this is the caveat I want on record before anyone asks. So in the further slide 12 is going to show classical winning decisively at the 12 to 20 qubit range we actually tested. The crossover, if it ever comes, lives well beyond current hardware. Characterizing exactly where the gap sits right now is the actual contribution of this project. So quickly, what's actually inside these circuits? So it consists of Hadamard gates, create equal superposition over every possible answer. A cost layer includes the optimization objective as phase rotations, a mix layer, either standard X rotations or my constraint-preserving ring mixer, which I'll get to. It eventually explores the solution space. That block repeats 3 times before measurement. 3 reps, 12 qubits is the depth I validated everything against. Now coming to the portfolio formulation. So this track minimize risk adjusted cost subject to holding exactly B assets out of a 12 asset universe spanning equities, fixed income, commodities, alternatives, and cash. And I want to point out one thing. The expected returns aren't made up. They are anchored to Vanguard's own published March 2026 capital markets forecast. Volatility and correlation are documented assumptions, like flagged explicitly as assumptions, not fitted data. Here's a bug I want to own, not hide. In the Qisket's quadratic term dictionary needs of diagonal covariance terms double to correctly represent this objective. I missed it once. I only caught it because I cross-checked against brute force on a small case, which is exactly why that validation step isn't optional in this project. Brute force and the exact eigensolver agree exactly. Negative 0.1803. A single QAOA run landed 3.6% of that, with 2 of the 4 assets correct. Then I tried something cheap, multi-start. 8 independent runs, keeping the best, 40 seconds total, no new technique. It found the exact optimum. That's the number I actually want you to remember from this slide. A free classical fix closed the entire gap. Now, adding 4 real sector guardrails, equity, fixed income, commodities, plus alternatives, and cash, plus turnover cost against a prior portfolio, the turnover math is worth a sentence. I priced it with an exact identity that needs 0 extra qubits versus the general case which needs auxiliary variables. Recommended portfolio holds 6 assets, all 4 guardrails satisfied. I need to address one limitation over here. In a very candid sense, this constraint problem grew to 17 qubits and QAOA timed out there. You'll see exactly why on the scalability slide. I'm not hiding that this constrained version only has a classical answer, not a quantum one, at this size. Okay, moving on to the staffing formulation. Second track. It minimizes labor cost plus a coverage gap penalty. One shift per agent, skill specific coverage, sales versus support, not just headcount, because that's what the brief actually asked for. Second bug, and this one's a good story. My coverage penalty was smaller than labor cost. The QUBOs true minimum was higher. Nobody, like mathematically it is correct, operationally it's useless. Same root cause as the portfolio bug, independently rediscovered. Penalty coefficient this time have to dominate the objective scale, or the solver finds a trivial cheat instead of the real answer. So same validation pattern here also. Brute force and exact eigensolver agree at negative 2184. Single QAOA run 14% off. Support coverage short on one shift. Multi-start again, 8 restarts, and 6 of them found the exact optimum I was looking for. Same finding as portfolio, a free classical fix, not a new quantum technique, which perfectly closes the gap entirely. That's a real pattern across both tracks, not a coincidence. So, okay, stretch. Stretch goal. So support demands hikes, spikes 40% mid-shift. Can the system react? Cold resolve, 4.3 seconds lands on the new true optimum. I tried warm starting from the pre-disruption angles expecting a speed up. It didn't help. And I want to explain why rather than just report the negative result. Cobila runs a fixed iteration budget no matter where it starts. So there is no time saved actually. And starting close to the old optimum actually anchored the search near a local stale optimum for the new problem. Yeah, it landed 1,000 points worse than starting cold. So the defensible claim that survives is simpler. A full cold resolve in 4 seconds is itself a legitimate live reaction capability. And the resolve surfaced something real operationally with all 4 agents already deployed. The spike forces an actual manager trade-off, overtime versus a coverage gap. That's not a solver failure, that's the real constraint. This is the central finding of the whole project. So I'll slow down here. Both tracks tested completely independently, hit the same wall in the mid-teens to 20 qubit range. Portfolio at 12 qubits, QAOA comes back infeasible, 5 assets selected instead of 4, even with a properly scaled penalty, and at 16 to 17 qubits, times out completely. Staffing at 20 qubits, the process gets OOM killed, pause, for a while. Meanwhile, classical exact solving stays under 2 seconds the entire time. At this problem scale, classical wins on speed, optimality, and feasibility simultaneously every single time I measured it. I am leading with this because I'd rather you hear that the honest ceiling from me that assume I'm hiding it. Now, coming to the validation part of real hardware. I didn't stop at simulation. These circuits run on real IBM hardware. Fez by the Classiq IDE, two versions of each, a single training run and multi-start. Single run portfolio consists of 10.5% feasible on real hardware and in multi-start 15.8%. And the best answer found was essentially the exact optimum. Staffing is the more dramatic case. Single run found a best answer of positive 200, badly wrong. Multi-start found negative 38, 3184, the exact global optimum and nearly doubled the feasible rate. I'm again repeating it, it nearly doubled. That's the clearest result in this whole project. A free 45-second classical fix measurably improved outcomes on real quantum hardware, not just simulation. Here's a more fundamental fix than tuning. Standard QAOA mixers can wander anywhere in the search space and most of that space is invalid. I built Hamming weight, preserving mixers following Hadfield et al. For both tracks, which structurally cannot leave the feasible subspace. On a noiseless simulator, that's a mathematical guarantee, 100% feasible, every single time, verified over 1,000 shots. So, real hardware is where it gets honest. Portfolio's 12-qubit ring mixer held up reasonably 16 to 19% feasible. Staffing's 16-qubit mixer dropped to just 1.2%. Here's the mechanism. Not just the number, these mixers need extra gate types that each decompose into roughly 2 CNOTs on real hardware. And 2-qubit gates are the dominant error source on NISC devices. The bigger catch is like more complex circuits pay for that guarantee with more noise exposure. The theoretical guarantee is identical either way. What differs is how much real gate count it costs to earn it. One more experiment, and I want to be honest that this one came back inconclusive. My hypothesis, building the mixer from Fez's actual physical qubit layout instead of an arbitrary ring, should reduce the overhead from routing gates and improve real feasibility. So the result, 18.9% feasible, right at the top of what the abstract ring already achieved, not meaningfully above it. My best explanation, the hardware-aware version needed a much deeper transpile against the real backend, nearly 5,000 gates, and that extra depth likely cancelled out whatever it saved in routing. But here's the genuinely striking part. The single best answer the circuit found on real hardware was the exact global optimum, better than what the noiseless simulator itself converged to during training. Connectivity alone isn't the bottleneck. Total gate count matters just as much, and I didn't expect that going in. Pulling this together, the scale gap is real. Published QAOA portfolio work runs 4 to 8 assets. Institutional portfolios needs hundreds. NISC noise is loss sensitive to small errors, and I quantified that directly across 7 real hardware circuits. And there's a genuine open frontier. Multi-period rebalancing, real-time disruption replanning that's under-attempted even classically. And to my position plainly, I didn't chase an overclaimed speed-up. I characterized exactly where quantum stands today for this problem class with reproducible numbers, not citations, and built 4 technical contributions on top of that honest foundation. The skill-specific staffing formulation, constraint-preserving mixers for both tracks, the hardware-native topology test, and the measured multi-start hardware improvement. Okay, so let's switch on to the live demo. I'll open the live demo, though it is a Streamlit open page. There you go. So this is live, not scripted. I'll move the risk aversion slider to just to realize the portfolio co-pilot, and there you go, it generates the result in real time. There's the allocation of the assets divided equally between equity, fixed income, and cash. Now switching on to the workforce planner, likely I'll adjust the slider, and then with the simulate demand spike checked, I generate this variable. So this is how it generates in real time. For the shift S1, S2, and S3, assigned, short, converted, and covered, as well as we can download the CSV file format, the data we have got. Okay. So every number on this dashboard traces to the classical exact solver as the operational answer. QAOA is shown for comparison, never as the thing I'll actually deploy. All right. So now coming on to the presentation. All right. So I want to spend 30 seconds on what I chose not to build, because I think that's as informative as what I did build. I tested parameter shift gradients for QAOA and rejected them with a measured number. 540 circuit evaluations per gradient step against Cobila's entire 300 iteration run in under 6 seconds. A 50-step gradient run would have cost 26 minutes per configuration. That's not a guess. That's a measurement, and it's why I didn't pursue it further. Quantum-assisted PINNs are a genuinely different problem class. Continuous PDE solving, not discrete combinatorial allocation. So I scoped that out early rather than let an adjacent research direction eat that timeline. Basket option pricing is related, shares the same covariance data, but answers a different question than this brief asks. So coming on to the limitations, all the financial and call center data is here. Here is synthetic. I want that stated plainly. Returns are anchored to Vanguard's real published forecast. Volatility and correlation are documented assumptions. The portfolio encoding is selection based. All right, not continuous weight, a deliberate scope choice. This is single period only, no rebalancing model. And QAOA was trained on the free simulator with only the final angle submitted to real hardware. I didn't run full optimization loops on hardware. That was a CPU hour budget decision, not a technical limitation I'm hiding. So coming into the closing note, if I had more time, multi-period rebalancing is the biggest open piece. Real portfolio management needs transition cost-aware decisions across periods, not one-shot allocation. I'd extend the hardware-native routing test to Staffing's larger mixer. I'd apply multi-start, which measurably held the baseline circuits to the constraint-preserving mixers too, since I only tested it on the penalty method versions, and I'd push the disruption resolve toward realistic call center scale. Hundreds of agents, not 4. Thank you.